Hello, hello, just setting things up here. Alright, there we go. Don't have much time today, like a little less than 2 hours, so let's see. Okay. Well, we'll see. Maybe I get more. We'll see. Okay. Had a little bit of a break. Now let's get into it. So yeah, we were in the middle of updating in our IR language here, like upgrading the memory stuff with heap stuff, and let's see. Yes, so there are some issues now with, so I believe the basic pipeline. Okay, let me just double check here. So this one does not work. Unsupported streaming. Okay. So I believe this works. Yes. So the normal thing works, but the basic pipeline does not work. So I'm trying to figure that out. Right. So this is kind of how it was before. Like we got. So we have this stream instruction, whose purpose is kind of like a blocking instruction that will block and kind of forward the pipes, like read from the pipe source and write to the pipe destination until the source closes, which will cause the pipe, which will cause the stream to then not block anymore. Unless the, I guess, well, there's an option on the pipe that could also prevent that. Like you could have a pipe that is open all the time, which means the stream won't or will always block until the option is turned off. Yo Penguin, what's up? Welcome back. Yeah, and as we can see before the memory update, we did the resolve value, which kind of was like a magical catch-all thing that would either look at the value as a literal value, or it would also dereference if needed to try to get something that we can stream, which should always be, of course, a pipe. Now we're kind of saying that, okay, well, we should always put I think a pointer to a pipe in the stream instruction. So now we're using resolve location. I'm just gonna log this out to see what this. Oh yeah, actually we do see streaming here. So if we just say this, we can see that, okay, we get an address which is it's like a pointer. So let's look at resolve location, because I think, yeah, the location should have dereference in it. So let's look at where does this actually happen, is the question. this happens somewhere. Here, I guess, maybe, yeah. Okay, so it's the normal. So let's look in the compiler. It's in the compile initial. It's like the kind of this main runtime, I guess, of the program. So yeah, here. So this is what we put in there, which is a dereference to the stack 0, which makes sense. That's like a pointer to the stack. Although then the question is, like, what is that then? Is that a pointer as well? Because when we fork, we also provide the pointers here, right? Okay. So then that depends on the fork instruction evaluation, actually, what we add to the stack. So here we resolve location to standard in, which I think should be, yeah, that should, okay, that should be the actual pipe handle. So I'm confused there. So let's go through this again, and we'll go down to whenever we get the first stream here. Should be here. Okay, and now, actually, okay, no, I'm lying here. This is not compile initial. This is, as you can see here, this is set to thread 8. So this is not the compile initial. This is actually later. But what we can do here, we can see on the stack we have stream S1, right? And that's a 0 there. That's curious, like address 0. Okay. So then, so set to thread 8. That has to be like a compile pipeline. We create a pipe, right? So that's on the stack there. And then we set up all the stages. Right, and then here we inherit standard out stream set. Okay. So standard out stream set, yeah, that's the same set. So that's set 2, yeah. That makes sense. And then, but then the standard out was actually set to 0, which doesn't make sense. Like the address 0. Yoko Guy, what's up, what's up? Welcome back. We'll see how much time I have today. I think I have like 1.5 hours from now. It depends. Yeah, I don't have much time today, unfortunately. Maybe I'll have more tomorrow. Yeah, it looks like I have a little bit more time tomorrow. I just wanted to get into this real quick here. Let's see, and fix this last thing here, because it feels like there's, with the memory stuff, memory update, it's like it feels like there's not that much left on it. So I just wanted to kind of see if we could finish that off here today. But I am confused here a little bit, actually. Okay, you know what? Let's go through this again a little bit more carefully now. So we have these forks, yes. Okay. Because now I want to say standard IO. Skip. Okay, so now that skip is off. So now we can see the next thing here is actually, you know, this. I just wanted to see what the stack is here, what the stack looks like. Okay, so let's turn this off again. Or skip, I mean skip. Yeah, skip is on. So there we go. Studying Java Spring Boot. One of Uncle told there is role in this company. Oh, nice. That's good. Yeah, good for you. It's going to be done. Well, yeah, I mean the kind of the memory update that I did, which will lead to, like, when I restore functionality of this memory update, that will lead to being able to create those, you know, those strings that we have for, like, string interpolation, like creating those strings and having that the string being represented in like heap memory. Because right now it's like it doesn't work having those like strings with interpolated values in them. Doesn't work right now. So I needed a heap mechanism to be able to like allocate memory, and so I'm doing that update right now. Yeah, string operation, but it will also lead to other things like keeping you know, kind of like dynamically sized things like arrays, like concatenating arrays, doing all that stuff would also be possible with this memory update as well. So, well, it's the foundation of that anyway. But yeah, we need to make it work here first with the existing stuff, and then we'll get to that. Okay, so here's forking to the first stage, which will fork. And here we can see, I think it's this fork that then goes wrong. So this fork is like is trying to inherit. And you can see here also like we have 0, 1, and 2, right? So 0 goes into pipe number 3. 1 goes into address 0, which already is wrong. I'm not sure how that happened. Let's actually go back and do this again. So these are the 3 standard IO stuff forks there, yes. Then we have a pipe that we create, or we create the space for it, and then we have the pipe that we create there. We set a pipe option, keep open, true. We now fork here. So here we can see the issue, I think. So we're forking, we're giving a pointer to stack 0, a pointer to stack 2, but then this one is not a pointer. It looks like it's the ref without being dereferenced, I think. So that's okay. Let's try and figure this out. Which would be I think it's here. Each stage is it's compiled, and then no, it's over here. Yeah. So standard in, and here's the ref here. Yeah. What languages do you use in the day-to-day job? I use TypeScript, and well, it's kind of different on the back end depending on which project, but it's C# mostly, and for some reason there's like some F# in there. And but that's for like a subset of things. And there's some TypeScript on the back end as well. There's a couple of different things, but it's mostly C# and TypeScript, like C# on back end and TypeScript on front end. And of course, now we're doing a lot of like you know, AI stuff. So, or we're using AI a lot. So there's a lot of like we're trying to like integrate that into our workflow more and more as well, which is pretty nice actually. I mean, if you've got something that doesn't really require like top-notch code, I mean. We still have to kind of investigate whatever code the AI puts out, of course, but for the most part, like it's just a quick glance and it looks good. The hard part, I think, is like, or the thing that you want to learn is like saying what the correct things to AI so that it would produce the correct stuff, because it's easily misinterpreted. Like, yeah, I won't get into all that stuff right now, but it's pretty interesting times we live in right now. Like it's like a shift right now. It feels like we're living in. We'll see what happens though. Maybe the bubble pops and we'll all be left without AI or something. I don't know. I don't know what's gonna happen. So. Let's see. Okay, so this ref here is maybe then. So what is this array here? This is locations. Yeah. So where do we append here? We append somewhere. Or no, we just have an array, right? Stage sets. Where's the refs? Over here. Okay. So yeah, so we're doing like new ref that gives us a location. This location is absolute ref. Yeah. So that's not a pointer, right? But here I added this dereference function to the location, so it's kind of like a pointer, and if you want it dereferenced, you add this dereference thing here, because otherwise it will be just the address itself, I guess. And so when we're doing, where's the fork at? Over here, yeah. So when we're doing this, we should do dereference as well. There we go. So now we don't put like the address in there. Also, I would like the, I have to see if this is also correct, but I would like to, because when it's like printed out, it just said 0, which is kind of weird. It should be more like, yeah, it should say like, okay, well, this is a ref. Although, yeah, the stack. Yeah, there's something wrong going on there. It's like it said address and it points to 0. That's wrong. But okay, let's just see if this fixes that issue. And I think these, if we add more stages, we will go into here as well, which will also be wrong. But let's try this first. Okay, we got another issue here. So let's run this again. What do you mean product any clue? Three is void? That's strange. It should be like a pipe. Okay, well, apparently, why is 0 pipe 3? Like standard in is pipe 3? That doesn't make sense. No, what the hell is going on here? Are we overriding? Wait. Okay, we got pipe 0, 1, 2. We're creating a new pipe there. So here's where we're setting the pipe to SF plus 1 plus 0. Okay, there you can see we overwrite that. So because this is plus 0, which is not correct. For some reason we get like plus 0. That's the we get like the incorrect address for this ref here. That is strange. Yo Blue, what's up? What's up? Did you see the video? Yeah. Do you mean the one with the icons fighting, or? It was kind of funny. Welcome back. What the hell? There's like an ant on my... Or is an ant or a spider on my curtain? I just saw it. Okay. That's weird. It's probably a spider. There won't be ants crawling up here. Okay. All right. Anyway, okay. So when we create this ref, okay. So what's happening here is that, yeah, we're looking at the current frame, and then we're taking the relative stack counter, adding that there. Well, we're doing that at the end. So for some reason that is wrong. I think it's probably I changed something with the frames. Top frame. Okay, well that's the scopes. That's fine. Yeah, it's a little tiny spider. It's not the smallest spider I've seen, but it's also like here up where I live, like, or in this whole country, you don't get large spiders. I think the largest are probably about, like, I don't know, centimeter, a couple of centimeters or something. I don't know. It's moving though. No, it's like stretching out. And I don't know what it's doing. It's standing still basically, but it's moving its legs or something. I don't know. Compile initial statements and instruction. Okay, let's look at this one. So did we say? So yeah, we did add a frame here, but no instructions. Yeah, because the stack frame register starts at 0, so we don't need an instruction to like push a frame, but we do need it for our like internal compiler setup. So we have a frame that we can use here, but we don't have any instructions for it. So that we can keep track of the relative stack counter. Okay, but then we add these forward standard IO, which should be setting then 3 stack frame things. So the stack frame counter should be increased by 3 at this point. Or is it later? Actually. Oh, wait. No, yeah, it should be increased by 3. But then we have the fork, which also increases by 3. Like in the new instructions set. Yeah. Okay. So let's see now what this will do. Right, so now we can see stack counter is 3. Stack frame is 0 still. Well, that's fine. We get a new thing. Now we see that the address is not stack frame plus 0, it's stack frame plus 3. And now this one is correct. Okay. So I'm gonna just continue here and hope that everything is fine. Okay, well, we still get some issue. Okay. Let's see where this is happening here. So we're at exec. Okay. Exec. Evaluated 349. Okay, so let's go over here. Right. Okay. So yeah, they should be yeah, okay, so there is something wrong now. Okay, let's look at the compiler. Let's go to compile pipeline. And double check the last stage. Oh, here we go. So here we need to dereference as well. I also will say this needs to be dereferenced and this needs to be dereferenced as well. Okay, there we go. There we go. Awesome. Okay. And here we can see the instructions. And yeah, I mean, yeah. It should all work. I'm just gonna go through just so it makes sense. So set4 will fork to the thing that will execute echo hello. We will push the resulting thread handle to save it, and then we fork the stream. For that pipe, we pop to get the first thread handle back. Maybe we should do it the other way around, but I'm afraid that, because then we don't need to do the push and pop. However, I'm afraid that this will close immediately if we do that. So I want to fork it first, just in case, and then we'll wait for this thread, which is executing echo hello. And then after that is done, we close the stream. Okay, set5 is executing the thing, so we're pushing the arguments, pushing 1, executing, waiting, so that's fine. Yeah, that should be good. Okay. Yo, Vincent, welcome back. Yeah, I'll just refill my coffee. I'll be right back. Awesome. Okay, so now okay, let's do some other tests. That seems to work. What else? Blocks. Does this work still? Okay, so this one does not work. Let's check out compile block. And see if there's something going on here. So we have this pipe here. Important that we dereference now. Also, okay, the block. I want to see, is the block in its own thing? So this one creates a pipe. Yeah, this is the pipeline. We're creating a pipe. We're forking. The first stage should be the block, and this should be the second there thing. And then waiting for the last thing there, yeah. Here's the block stage. And see, this doesn't have, the thing is here, we don't have a stack frame, although it should be, since it's a new thread, it should be 0, so this should be correct. Yeah. Because you can see here, like stack frame plus 0, this is like a new, we're creating a new ref, which refers to stack frame plus 0. So in this case, stack frame should be, no, actually it should be 3. Okay, hang on. Creating a pipe, populating, setting option, forking. Okay, pipes look correct. Creating a new. Wait, why does that say? Oh, because we're in a different thread. Right. Forking again. Now we're back here. We're creating the pipe now. Okay. You're forking again. This looks kind of weird, but it's basically just forking and then waiting. But yeah, it's fine. And here we're executing grep. Now we're back to main thread. We wait for the last thing. So now we can see the stack here, although we don't actually see it because there's too many things going on over here. Okay, well then let's print out the stack like this. And we should see it for thread 1, 2, 3, 4. Yeah, it says, but it says void here. Stack frame plus 0. Yeah, see, this is the same issue here. It says plus 0, it sets a 0 thing. So that's the issue. So compile. Compile pipeline. So when we do fork, this is for the first one. This is the intermediate one, so it should be the first one here. We do the fork. Which adds 3 to the current frame. And the current frame is per instruction set. But when is that frame added, though? I think it's added when we create the set. Yeah, stage set 0. So it's added here. This one creates an instruction set. We just append a new set. Then we push the frame, no instructions though. Okay, so that's fine. I'm just going through everything so that we can see that everything should be fine. Oh, wait. And okay, so the issue here is that we're looping through here to create these stage sets, we compile it, but this compilation is now in the context. It has the wrong context because we're creating the fork here, which changes the context of each stage set. But this compilation happens without that context change. So we actually kind of need this to be done first, or yeah, but we don't have the set though. I mean, I guess we could loop through, set the stages first. Okay. So we set stage. Right. So we have that. And then we do the fork. Because what's happening here is we're looping through all the stages and basically compiling them. We're compiling over here. And then we're going back to original set and then forking. But we could just as well fork before. Do all the forking before. The problem though is we don't have the refs. Well, do we have the refs? Yeah, we have the refs. Okay. So we have the refs, we have the stage sets, yeah. So we'll just move the forks. I just need to make sure everything is looking good here. We'll move the forks into here. No, not in the loop though. Outside of the loop there. I just need to make sure we have everything we need for this. So this should be fine. And then this is fine. Okay, and then we have the last one as well. The last set is created here. So actually we'll move this up to where we create the stages, the stage sets. So we have all the sets created here. And this is the last compilation stage, but this one needs to be moved as well then. Over here. Okay. Just to make sure that all the stack counter is correct. Because part of when we're forking, when we do a fork, we actually increase the stack counter by 3. So we have to do that. The first thing that happens should be the fork. But that happens like in a separate. This is kind of weird, though. This doesn't make sense, though. Yeah. So just as an example, now if we go back to this one, we should see that, well, if we do like standard IO skip, we turn that off. Here we can see that the stack counter is 3. Makes sense, right? Because we have 3 things on the stack. However, let's go until we do the fork. Actually, let's do standard IO skip so we can do it a little bit more quickly here. Fork, yes, fork, push, wait. I think I have to redo this. Fork number 4. Why is this empty? Oh, because I changed stuff. Okay. Oh, right. We don't create the sets again, of course. There we go. Okay. Anyway, let's go back. Oops. Okay. Where's the fork? There we go. Now we got the instructions. Okay. So. Hello, Ayeshyam. What's up? Welcome. I am a code streamer. Yes, I guess you could say that. Did you already write the Lexer parser stuff? Yes. Well, technically I didn't. The AI did. Well, okay. AI did the kind of the foundation, and then I took over and built on it and replaced a whole bunch of stuff as well. But yes, the Lexer parser stuff is basically done. There might be like, but there are more things that I need to add later. But if you want to look at the code, it's available on GitHub. The link is, the link is in the description. Lexer parser. It's like these components. You can say it's like chunks of code that will create. That job is to take the source code of your language that you're trying to create, and so it takes like a source text file code, like a string of bytes, and it turns it into, something that is more manageable to reason about. When trying to compile it or interpret it. So basically, you could take, like, let's say you have in your source file you have a string, right? Now in a source file, that's just a stream of bytes. But the tokenizer or the Lexer will actually turn that into kind of like a string context. It will package it into something called a token. So it will tell you, like, yeah, this is a string and it has this content and it's located in the source file at this location. And then the parser will take that and turn it into like an expression package. Yeah, it's parts. It's like parts of the compiler. That works with the source file, you could say, or source file / files, whatever. Let's see. Okay, I just want to demonstrate this because now, this is not important. Yeah, let's skip through this. Okay, you're sleeping. Okay, now is important because now we're forking into set number 2. The thing is, the fork operation itself does push stack counter by 3, which does not make sense in this case because we already forked into set 2 previously. So when we now step in here, actually, standard IO skip. Yeah. So we'll get to thread number 2. Okay. Actually, stack counter is still 3. Okay. I was wrong. I thought it would increase the stack counter. It didn't. Interesting. Maybe it... Oh, I see. Okay, yeah, it didn't increase the stack counter, but it did increase the relative stack counter of the new things pushed on the stack. So if we would push something on the stack after that, that would have the wrong address. So that's what I mean, like the fork instruction should not mess with this here. That should happen like when we create a new set instead. Or wait, should it? No. I think what's going on here is that it's not the... It's okay. So these frames are like connected to the sets now, which is wrong. They should be connected to the threads. Okay. Excuse me. Well, it's not really a problem right now because it just so happens that we don't really use it in this way, but it could become a problem, and I need to kind of think about how to do this. It's we could also not store the pipes on the stack as well. We could store them somewhere else, like on the heap or something. Okay, I'll just put a to-do here since it's not a problem right now. I just thought of this. This will become a problem. Okay. But that was not the problem. What was the problem actually? Oh, the problem was that the ref. Okay. So I think this should work now. No. Unsupported streaming address. Okay, so there's a thing there. Okay. Let's see where this happens. Okay, +3. That's correct. Pipe option +3 should be correct. Thread 4, yes. And then same thing. Same thing again. Wait, why are we? It feels like we're stuck here. No, it's just a whole bunch of pipe options we're setting, right? Okay, that gets executed. Great. Pipe forward +3 to stack 1. Sounds good. Wait. Yeah, I guess. Now we're forking the stream, I think. No? Maybe? Okay, here we go. There's the issue here. Thread 8. Thread 4, which is like the first stage, is forking. Ah, this is okay. So this is the block. Yeah, the block compilation. Okay. So we have this pipe. So is this not dereferenced somewhere? Here. There we go. And there we go, it works. If we run this, blocks. There we go. Cool. So it does work, so we don't need to worry about that. And if we just cat it, it should also work. Yeah. Cool. What if we bash it? That works. Okay. Hello. Is C better than better or zig? I can't set up zig. I can, but whenever I take input, it gives error. I would say yes, it's better than zig. Or I mean, sorry, the other way around. No, but it you know what's better? It's kind of very. I think it depends on, you know, if you take a developer who knows C, of course, and not zig, then it would be better for that person to use C if you want to be productive. But I mean, in the context, if you want to say like, okay, well, does zig have better features or whatever? I mean, I would say like zig is like more modern, and it also does interface with C. So I mean, you know, if you think that you could work with zig, you could try it and see if it works for you. Do you know C? I guess would be a question that's relevant. Zig is very close to C, so it's like there's a lot of overlap. But then there's like things you can do in zig that you can't do in C, and also vice versa, I guess, as well. But yeah, it's not an easy question, you know. I would say that zig is like more modern. So if you want something that is like easier to work with, I would probably get zig. But however, there's a caveat there as well, because zig is not like it's not fully, you know, it's like still in like, I don't know what to call it, like beta or whatever. So it's not, you know, it's not released fully, I guess you could say. I mean, you can use it, but it's not like feature complete. So, and there's a lot of documentation missing in a lot of parts. So it's not an easy language to use right now, especially if you're a noob, or if you're like a junior, or like, you know, if you're just starting out learning programming, it's not a good language to start with, I wouldn't say. You have learned a lot of zig when it comes to input part that gets standard in. Can you demonstrate how to take input, which version? So I'm using 0.15.1. So I'm not using the latest 0.16 because that's not like released yet, or at least not when I checked last time. Let me check that actually, because it might be just around the corner. I don't know. No, it does not seem to be released yet. No. Okay, so I'm using like the latest non-master version, like 0.15.1. Although there is a 0.15.2, but that's not... yeah, I don't know. There was some weird stuff with the release of that one. But let me show you, because we do use standard in here. I mean, I'll just do like standard in, not zig here. So standard in, it kind of depends on how you want. how you want because by standard, I think if you're not in like raw mode, you will take like standard in line by line. So I guess it depends kind of on the terminal. But let's see if I remember now. But basically, you start out with a standard IO file. So this would be file standard file system file standard in. So now you have the kind of the SIG version of a file, which represents standard in. And then you want to have a mutable reader or a file reader, more specifically. So this would be this is the important thing that you actually need to have. That you need to have a mutable version here. So you just say reader there, and then you also need a buffer, because otherwise there's like strange things happening if you don't have if you have like an empty buffer. So I usually always have like a buffer. So what you can do is you can just create standard IO buffer, which is a mutable array of, let's say, a kilobyte. So there you go. Now we have a buffer. Okay. So now we have a buffer. We have a file reader. And then if you want, now you can access, you know, the reader interface directly by saying .interface here. And then you can say like read, you know, you can say like take delimiter exclusive and new line. So this would get you like a line. I think you have to try this as well. So there you get like a line. And then we will say, I'm just gonna log this out like this. You said line, and then we say zig run. This is never muted. Oh yeah, this needs to be an address there. Okay, let me do this here actually. Standard in zig. So there we go. Now it's waiting for input here. Hello, hello. And you press enter and it will give you the line there. What version are you using now? Why not take delimiter? What do you mean? Is there a take delimiter on the file reader or no? But yeah, this is how you set up a basic, well, yeah, standard in reader. Oops, standard IO. This should be standard in. Sorry. Was this 0.15.2 or 0.16, which I think was the problem? You should be able to use 0.15.1, or I mean 0.15.2. I'm not sure about 0.16 because I never used it, and they did change some things with, like, I'm not sure what they changed, but there was some changes to like with the like the async await stuff. Yeah, okay. Yeah, sorry. Nightbot does not like links. I think I want to like change that behavior. But that is probably because it's on master. I'm not sure if that exists. No. So that only exists on 0.16. Not on 0.15, which I'm using right now. So I guess they made those two functions into one. Like take delimiter, or maybe not. Returns the slice of the next bytes buffer later until it's found. The last is past the delimiter. Return slice excludes the delimiter. Okay, so take delimiter is like excluding the delimiter. So this is essentially the same as exclusive here. Yes, because I like using the version that does not change. Is it so hard to believe? Like I'm using like the version that's currently the stable version. Like I don't like using like the nightly thing. I want to wait until 0.16 is, you know, it's stabilized and released until I switch to it. Okay, but yeah, so this one works. Let's see some other things here. Exit. No. Oh yeah, I skipped 0.15.2 because it's not in the list of like official releases, although I think it is an actual release, but I don't know, it's just a minor upgrade anyway, so. Whatever, I'll just wait for 0.16 and then I'll upgrade to that. Runtime refs, no, that's the same thing. Why do I have so many of the same? Okay, let's try these ones. Okay, here we go. Oh yeah, because we don't have the string literals or the interpolations yet. Right. I think that's the next thing. This should be infinite. Okay, it is infinite, although it doesn't actually echo anything, which is weird. So that is a bug. I'll write that down. Okay. Maybe it's related to this, not sure. Alright, so now we'll go to bindings and we'll see what's happening here. This is of course still an error. It's an error when compiling. So let's see, 908. Uh, 0.16 is going to be a lot of refactors coming from downstream for downstream code. Yeah, we will see what happens. I mean, I've heard from one side that there's not going to be any changes to the interface, like the reader-writer interface. And then I've also heard that there's, well, I mean, there's going to be something. Although I'm not using like multi-threading or anything like that right now, so I'm not sure how much I'm gonna get. But oh yeah, one thing that was gonna change is you have to pass like a context around, like an IO context around for many of the I/O functions. Just like you have to pass an allocator around for things that needs an allocating memory, you need to pass I/O around for things, I guess, needing I/O stuff. Which is a pattern that's interesting because, you know, is there going to be more stuff later in the same vein? There's going to be a lot of things you have to pass around. But maybe it's stopping here. Maybe we can solve it with some kind of, because most things do need like both allocating and I/O in my program, although then we could make maybe a container for both of those, so you have pass around like one container that has everything instead of passing around like, yeah, we'll see what happens. I'm not sure. Okay, so here's the issue here, because we kind of disabled this part of the compilation. So basically what we're doing here is that we have string interpolation. So this is a string, this is a string, although this string is different because it has interpolation. So, but they are both string literals. And so what we're doing here is checking first that, okay, do we only have one segment? Now, what is a segment? Well, a segment is basically, if we have interpolations, we have multiple segments. So here's only one segment. Here we have two segments, although it's technically three because there's like an empty segment in the start between. So it's basically, each interpolation is like surrounded by text, literal text segments. So this part is a segment, the comma, space, world. So this is one segment, which is the literal text. And then this is one segment, which is just the expression inside here, right? So if we only have one segment, that basically automatically means that we only have a literal string here. So that is like handled separately here. Which basically is just adding this to the read-only data and making a pointer to that. But then we have the other case, which is if we have like interpolation here. So what is happening here? Well, this is kind of mixed in with old how it worked before, which is basically we created like a list. We allocated a list of things in the compiler memory, and then compiled things and put them in this list, and then passed that list over to the evaluator. However, now I want to do this like in the virtual machine instead. So instead of creating this thing in the compiler, I want to sort of support this this kind of expression in the virtual machine instead, and that's what we're trying to do over here. So instead of creating this stream list, we will create this thing here, which is pushed. This is on the stack now, so this is kind of like it's going to be like a pointer to the list on the heap. So here is the alloc instruction. The alloc instruction will create a thing on the heap. It will allocate this many values, so segment number of, like the length of segments, number of values on the heap inside the virtual machine. And then we will do what? Yeah, we'll set the ref to the thing. I think we need to dereference here. Actually, no, wait. No, we're setting this pointer. I'm not sure actually. We'll figure it out. So this will set this ref to this, which is the register R. Don't we have like init register? what is this? A value? Right, that's a value source. Yeah. Okay, so we're setting it to the R, which is the result of this alloc. So this alloc would put into the R register, it will put the heap pointer there. So then we're basically setting it on this stack space as well. So we store it there. And then we push the number of segments. Okay, I don't exactly remember my the algorithm here, so I need to go through this a little bit. Something like global constant, something. Yeah, we'll see how we will solve it. I'll just bear with me 1 second here. All right. Hello, Lenamir. What's up? Can we take integer inputs? You kinda can. I mean, yeah. you can, like, if you turn, like, you can't turn, you know, in like let's say you get a string from standard in, and then you can like use the standard format parse int or parse float to parse them into integers or floats. But then I think you have to kind of make sure that you pass in like a trimmed string that is a correctly formatted number. Okay, cool. Cool. So are you planning to convert like a project into Zig, or just go in and learn a little Zig? Okay, so we're having a new ref. We're allocating that. We're setting that. So now ref should have the pointer to the allocated thing. We're pushing the length of the segment. Yeah, so now basically on the stack we have kind of like a slice struct, because the first thing on the stack is the pointer to the string or the slice, and then here's the length of the slice. So this together forms the slice on the stack. Okay, and then we go through each segment. If we get a literal text, I had this code from before, so let's go through that, I guess. So we're setting the R register. So we're setting the R register to be stack frame plus that, which is basically the pointer to but that's dereferenced as okay. I don't remember why we are doing this. And then this is the part where we take the literal text and we add it to the read-only data, and here the result is the pointer to that. And then we set that to 0. Right, so that's okay. So what we're trying to do here is we're trying to set we're trying to take the pointer to the slice, dereference it, and set that to this to the result. And the way we try to do that is we're using the R register. I think was the idea. But let's see if we can do this. So I'm gonna say we're gonna set ref dereferenced, which should be now that should be the pointer actually. Okay, so I'm gonna do that. We're setting R to the pointer of the slice, and then we want to dereference that yeah. So this should be like I, and we'll set it to the result. Okay. Because it's kind of like we need to kind of dereference twice. First we need to dereference the stack pointer, and then we will need to dereference that. The problem is though that we need to actually do dereference here as well. Did I have that somewhere? Oh yeah, that would be like options. So add X and then options. Dereference is true. Okay. Yeah, so we're setting R to the dereference of ref. We are creating, well, let's do this first. So we create the read-only data, we store it in the read-only data. We get the pointer there. We're dereferencing ref, storing it in R, and then we're dereferencing that pointer, and we also add I, so that we can set the correct value in the slice and then set it here. So it's basically, yeah. So it's basically we have like a ref, we have like a slice.adder. Okay, this is kind of like dereferencing the ref, and then we dereference. So here we're setting R equals that, and then here we're setting R dereferenced equals text. Yeah, so that's what's happening here. Okay. Been learning Zig for a long time because it looks cooler than C. I agree. It also looks more like sane to use. For you know, if you would, like if you're working in a C project, it would make more sense to use C maybe. But if you're doing something from scratch and want to learn a new C-like language, Zig makes a lot of sense. Although with some caveats, but I like Java and JS, more easy to do stuff in it. Zig cannot figure out syntax, too hard for me. Okay, well, I mean, the syntax is not that different, but it's like if you're, I think the problem is rather that you're used to that. You're used to like JavaScript and Java because those have kind of almost like exactly the same syntax, although not really, but also I think it's also becomes easier when you're more used, like when you've learned more than one style of language, it becomes easier to take in other languages as well. This is NeoVim, yes. All right, thanks. Good luck to you too. Let's see. I think I have like 1 hour left. Let's see if we can get this fixed here or get this figured out. So I think that should be it for the read-only text. So now we should go to the actual like this interpolation stuff. So it's kind of the same thing here, except what we need to store is the compiled expression there. Now, why do we do .source here? I'm not sure. what's happening there. Let's just do result. Will be an expression. Oh yeah, source is the value source, right? Yeah, because that's the thing that we have, and you are a value. Okay. So now we'll do the same thing here, and we might be able to avoid duplication here, but let's just figure this out for now. So same thing here, we're setting this to the pointer of the thing, which we probably should be. The thing is here, like, we're kind of overriding R. R could actually be used here as a return thing. So what we need to do is we need to store R in that case. So if the result is the R location, which would be like, where would that be? Location. Yeah, this one, which is not a, it's just that. Okay, so this would be a location, and then location would be, well, the ads would have to be a register. Actually, yeah, register. And register is equal to tag. There we go. So now we're kind of checking. Okay, well, are you the R register? Or we have the means to check it. So if you are register R, that means it's kind of like a thing that was stored that we need to save this result. So we're gonna say push result and so we push that, so now we have stored that. I think I wrote this down somewhere. I did write this down here. Yeah. So here's the kind of the blueprints. We see the same thing here. We have the ref. This is the string literal ref. We allocate 2 because we have 2 segments. Technically this should be 3, but this is just an example here. So 2, and then we set the ref to the result of this allocation, which is the address here. So we're basically setting the, we're setting string literal equals the address And then we're pushing 2, which is the length. So now the stack should first have the address and then the length. So it basically has the whole slice struct there. And then we are kind of looping through all the things, but this is I kind of wrote this down as unrolled. The loop is unrolled here, so this is actually a loop technically, but it's displayed unrolled here. So the first iteration is the first element here compiled. So we check if the compilation is using the R register. If it is, then we push it to the stack, we set it, and then that would be the result. The result would be the pointer to that segment result thing. And then we use this to we use the R register to set to slice address, like we're denoting here. And then we're setting that to the result, which is kind of what we're doing here. And then we're also checking here if result is R, we need to pop at the end. Okay. Now, same thing for the second element here. Okay. So it's basically the same thing, except now we need to add 1 here, which is kind of the same thing as saying /R1 is equal to result. I mean, the deref is, this is kind of like a deref in most languages anyway, so yeah, and that's it. And then we push that as an argument. I mean, yeah, then the result of the whole string literal is going to be this ref here. Yeah. Okay. Okay, so basically we do the same thing. The only thing that's different, we need to check if we're using the R register. In that case, well, here we push, but we do need to be able to refer to it. So I guess we do a ref, which is gonna be the segment. So this would be segment ref. Okay. And then we set that to R. So we set the ref. Now I'm actually not sure if I don't think we deref here to result. I'm just gonna double check this. So destination is a ref. Yeah, we don't actually care if this is dereferenced or not. Actually, we do. I'm sorry. We do care if this is dereferenced. So if it's dereferenced, okay. First, so the destination is the ref. Get ref pointer. Yeah. So that is already the stack. But if we want to dereference, we actually dereference if the destination is a pointer as well. We dereference, so it's kind of like dereferencing. First the stack pointer and then the pointer in that stack. Okay, but then we don't actually need to. Then we don't need to do this whole thing. No, because we can say dereference result. There we go. Yeah, this is gonna dereference twice. It's first like set it like the stack pointer, and then dereferencing the address inside the stack to be set to the result. So that should be good. Okay. And then that means over here that we're actually setting the stack now to this. Yeah. Which is that what we wanted to do? Yes, that is what we wanted to do. Okay. So that should be good. And then it's kind of like we're saying that, hey, the result of this compilation should be now this thing. So I guess we'll make this mutable. And if this is true, we're gonna set it to segment ref now instead. Although this is a value source, so we're gonna have to do a from here to turn the location into a value source. Very good. And now this is the ref. Now I'm not sure if we need to deref this or what. It's a point now. It's a pointer to the segment. That should also be a pointer to the segment. Although this is a value. It's a pointer though. Yeah, it's a pointer. Okay. Okay. Yeah, it's like a comp time known pointer, like address. Okay. And then, yeah, so we don't need to do this part here. We are gonna say self set, same thing here, ref dereference result, and then we check here again if this is, or actually we need to store this here, is result reg or then we also need to pop this because we're popping the, we don't care about the result there. We're actually popping this ref, yeah. So we're restoring balance to the stack. Oh, but wait, that means that we can't use this as a result actually. No, we're popping. We should actually use the R as the result in this case. No, yeah. So we're pushing here. We're setting the ref to the result. Yeah, so we're storing that. Then we're storing it in the heap here. Yes, and then we pop. So that's fine. Although I think we need to deref here because we shouldn't point to the stack. Yeah. Oh, wait. Yeah, deref there. Okay, well, we'll see if we need to fix this here, but yeah. I think that should be good. And then at the end, okay, so what do we actually return here? So we should return the stream is now a value slice. Yeah, that's Actually, I think we should just return a pointer here. We should just return a pointer. We should just return this ref here. Yeah. Oh, hang on. Wait. Oops. Ref destination. We apply the mod, and then dereference. We just dereference. Okay. I see. So we can't actually use this directly. We have to use the. Right, okay, so we do have to use the R register because we need to modify the address that we get. So actually we do need to excuse me. We do need to say init register R. So we need to set R to be ref. No, just yes. Think so. Ref. We'll do. So that will be the address to the stack. Yes. But then it's what if it's dereferenced? We get the val, they get the stack. So here we want to get the dereference. Yes. It's confusing because sometimes it means, yeah, here it means that we actually reach into the pointer in the stack and dereference that pointer, but here it means we're dereferencing the stack pointer. So this means different things. So that's why it's confusing here. I mean, I would guess that there are more jobs within Java, JavaScript than C. But yeah, that is that's a good point. Although it doesn't hurt to know. I mean, if you're new to programming, of course, and your goal, your focus is to get a job, then of course it's more important to learn whatever skill you need to get the job. But then when you get like, you know, you learn some things, you get hungry maybe for learning more, you know, then it doesn't hurt to get some perspective, like get some other languages in there. And because you could take whatever you learn from one language and use it in the original language that you were using, maybe in your job or something. You could do that as well. I mean, for example, both Java and C# has taken a lot of inspiration from functional programming languages during you know, the years. And yeah, that originally, those ideas, like in C# there's a thing called select, like collections. Those things actually comes from functional programming languages. So, and and yeah, you get a little bit of perspective, and you know, it's not, you know, bad or anything to learn like multiple languages. But if you're new, I think you should focus on the one language or two languages that you're trying to learn, because otherwise it's going to be too much information. You're going to mix things up easily, and I think it's yeah, it's probably better to stick with what you're learning. If you feel that way, that is. Okay. So we'll set it that's now correct, and then what we set here should be add and this is register R. So we'll add, and this would be I, and this would be deref true. So this is kind of like pointer arithmetic. R is set to the pointer of the slice. We add I to get the ith element. We dereference that to get the address, like, yeah, just to be able to set the address location to the result that we have. Okay, so now we're back here again. Turns out I did think about this, and it was correct the first time, so there you go. That actually often happens in the job as well. Like, you look at some piece of code. It could be your code, could be your own old code, or it could be someone else's code, and then you're like, hey, this looks weird, like, why is this done like this? And then you're trying to fix it, and then at the end it's like you come back around and you notice all these different issues that come up when trying to fix it the good way, quote unquote, and then you're coming around and you're like, okay, well, now I'm back to the original source code that I tried to fix, and I just spent a whole bunch of time doing nothing, basically. I mean, yeah, the one thing that you did was learn that the way that was done was before was actually necessary and not like bad code or anything. So it's kind of an interesting thing. It's like your mind is trying to see the simple path, but the simple path is sometimes, or very often, is like not enough. And also, I would say learning something different. Like, for me, this is not about getting a job within Zig. It's more like, for me, it's just fun. It's a fun experience to learn a new language, especially something like Zig that has something new to show, and some very nice ideas. And also, it's an excuse to also get more into low-level programming. It's a different feeling to program like this, I feel. It's like some things get harder to do, but then also other things get a lot easier, actually, to do. And I just love the fact also that all the structs, all the fields are public, so you can like go in and change, you can go into some kind of standard library struct and just change things to your own, like if you kind of know what you're doing, of course, you can do whatever you need to do. You don't have to kind of, make your own class that is gonna inherit this thing, and it's gonna override a function to do this other thing now instead, and then you just use the original thing and you just change the field manually. And there's just something good about that too. Like, yeah, this is better because it's way simpler, it takes way less time, it just makes sense. But then there's also, of course, things that's harder. I mean, the one thing that I would think about is the the garbage collection, of course, and some of the code abstraction stuff is, of course, harder in Zig. But then you learn to kind of work around it. You learn to work with Zig as well. Well, time flies here. Let's see how much time I have. Okay, so we got like 1 hour. Okay. Okay, let's see if we can make this work. So, where are we now? Value source. Right, so this would be from location. And init register. Right. What else do we have? Push length. Yeah, okay. So this is the correct intent, although it's not the correct thing here. So this would be a uinteger. There we go. Oops. Okay. Expected values found location. Right, so we do a from. Okay, that's added. We set R2 that we set the thing. You are a value. All right, we set that. Good. Here we compile results, we get source, we check if it's an R register. If it's using the R register, we store the result into this ref, and we then set result to be basically dereferencing the stack pointer here, and then we set R to be the slice address, because we need to do it again because this might change R, so we need to set it here to be up to date. And then we set the same thing here to be the result. And then we remove this ref from the stack to restore the balance to the force. And then All right, see you later, Penguin. And then what? I'm just trying to figure out if this is. There's so much going on here. I just need to figure. So what is going on is what I'm thinking is this result here. Now this is like a dereference. This is like a pointer, dereference pointer to this segment ref here. So it should refer to the content of the stack at that ref. I think. And then we pop it after. So at this point we're setting that. Yeah, that should be good. Okay. So that should be the pointer to whatever result we get. Or that should be the result we get from the compilation, basically. Yeah. Okay. And then the whole result is this ref. Now, the important part here is also that we return this ref. This ref is basically the stack where the string literal is defined. So the important thing is that the evaluator needs to interpret this ref as being two things on the stack, because this is the whole slice. The slice on the stack. This is the first value, which is the address. And then this is second value, which is the length of the slice. And then it needs to go into the heap and then get that number of elements from this address to build up the string. Okay? Because the string is basically just a slice of... It's kind of like... It's kind of like a tree. It's like a slice that is the root, and then each slice could have children, which could also be, you know, a string literal or something else. It could be anything basically. Because it's like any expression inside a string literal, but then it also tries to turn those into strings as well. Okay, but I think the compilation part is done. Okay, we got a thing here. There we go. Hello, nuclear ducks. Okay, I found it. You can change variables in real life. Okay. What kind of variables are we talking about? I'm gonna try to change a variable in real life by going out for a jog tomorrow. Probably. And that will be the variable, like number of exercises per week, hopefully going up. Okay, now we need to go to the, well, let's go and check what this will be. All right, we got all the, you can see here, you know, this is stored in the read-only section. So this part is stored in the read-only section. Here's the compilation here, string. So here's the string literal. Well, it's this one, I think, yeah. Because this isn't even part of the like the instructions. Like this is stored on read-only only, and this is like referring to the pointer. So this doesn't even compile to anything basically. It only it does compile to read-only data. But then down here we have this ref string literal, We allocate 3 elements because we have like an empty string at the start technically here, which I should optimize away, but I'm not doing that. Here we have like SF plus 0. That doesn't sound good. That sounds bad. Should be plus 3. Okay. But yeah, we're creating the ref. We are storing that. We're storing the result of alloc3 in there. And then we're pushing the number 3, which is the length of the like number of segments. And then we're setting now. And then, okay, so we have a loop, although we don't really have a loop in the instruction. We have like, it's like a loop. It's like an unrolled loop here. So we're setting the first segment. We're setting the, we're taking the address of the slice and setting it in R, and then we're dereferencing R plus 0. So this is kind of like setting the first element in R to the read-only. And you can see here it starts at 9, which is kind of interesting. It's kind of like we're storing an empty string in the read-only data that starts at 9 and then plus 0, which just means it has 0 length. So yeah, this basically does nothing. And then we have a fork here. Interesting. Why do we get a fork? Oh, I think it's because this expression, it interprets it as an executable, I think. Okay, well, yeah, so it's like set 5. If we go down and look at set 5 here, yeah. So it's pushing like 0 plus 5. 0 plus 5 is echo though. No, it's hello. Okay. Wait, why is it pushing hello? Push 0? 0 arguments? Okay, this is super weird. This is very weird. It's like executing hello. Okay, like a hello as in like an executable. But okay, forget about that. I'll need to fix that. But then we are creating a ref for the segment. Now it says +2, which I guess is correct since we have 2 things here. We have ref and push. Okay. So we're storing the result in R because this was a result. This was like a it's using R to store the thread handle of the fork. So we're saving that, and then we're setting now. We're using R to refer to the string address, and then we're saying the first, like the second element technically of the string to be, or this kind of string literal slice here to be the segment ref, yeah, the dereferenced thing there. And then we pop this off here, yeah. And then we're setting our, again, right, now this is the third segment. So we're setting this again, we're setting the element number 2 to this read-only data here. And then we push string literal +0 to, yeah, and then we push that and push 1 and then execute. Yeah, and then we wait for that. So yeah, but the problem is Problem is then that the compilation of the string literal actually increases the stack counter by 1, which is not ideal. It should actually, we should have it on the heap maybe, and then just return a pointer to that. Actually, it increases stack by 2. Yeah, that's an issue. And then when we're okay, so it's actually an error down here. We're trying to dereference this unsupported dereference valid type. Okay. So actually, I think what we need to do, we need to allocate +2 here. No, +1. Yeah, +1, because we want to store the length as the first element. So I want to set actually this would be like init abs register r dereference true. Okay, we set that because this returns this sets r to the pointer of the in the heap. Then we dereference that to set the first element of that allocated slice to the length of the slice. So I think that's what we need to do here, because we can't increase the stack with this compilation. We have to restore the stack. So we'll store this on the heap, and then we'll return the pointer that points to the heap of the slice, and then we'll interpret the first element of the slice to be the length of the slice. And so this would be from value, so the length would be u integer, no, not 2, string literal segments. Okay. And then I don't really think we need to have this on the stack. No, yeah, we do need to have it on the stack because we do need to save the allocation. Yeah. We need to have it on the stack. But then we need to actually pop it at the end. So we're popping that off the stack, and then what we return is actually going to be the R register actually here. So this will be the result actually, yeah. There we go. Because this returns the R register as a location, then we return that. Okay. Yeah. But then there was something weird going on. Oh yeah, okay. Let's try this again. Yeah, there was something weird going on with the compilation of the S here. Over here, we get a fork, which we shouldn't get. We should just get the pointer to the read-only thing. but now we get like alloc 4, and then we set the first element to be 3. Yeah, that makes a lot of sense. Okay, and then we get down here, it's gonna crash over here, same way. Okay, so let's check out why are we getting like when we compile the identifier, basically, I think it's like a call actually. We get, I think, do we get a slice? No, it should be like an address. Let's see what we get. Print AST. What was it called? Bindings. So here we can see arg0 is a literal string, segment 0 is text, empty interpolation, call the identifier s. Right, so it's an identifier. Which should be stored as a read-only data location. So I'm not sure why it's treated as an executable. That is strange. Because this gets into compile, then we should get an identifier, and then if we don't find it, we get an executable. Okay, I guess that's why. So for some reason we don't find it, I guess. So let's look at the binding declaration. And we should have an identifier. We compile that. So this should be the address to the read-only data. We declare that in our scope. And then we do the lookup, which, okay, so it might be that this just doesn't work because this, I haven't tested this yet, I think. So it's like we're looking up the name and we're gonna loop through to get frame by tag bindings, depth, yes. So we're going like backwards through the frames, and we're looking if they are, if it's the tag, then we return that with the index. Wait, wouldn't it be index and not? Oh, that's the depth. Right. And frame. If we didn't find it, we return null. Right. Otherwise, we continue over here. Okay. So we should have a bindings frame, because otherwise, when we declare, yeah, this would be an error. So we should have a binding frame. Wait, depth 0. And then we go backwards, yeah. depth start at 0, of course. And we get a frame, like if this exists, we return it, otherwise we continue and try to get the next frame on that same depth plus 1. Makes sense? But okay, let us do this. So I'm gonna do this. Not found. Identifier not found. Just to confirm that this is what's happening. Echo not found. Okay, so apparently it only does it for echo. I mean, I guess that makes sense, but why do we get an executable for S? So we're going to call, we compile the call, it should be, that should be, so the call, it should be an identifier S. And then let's assume that this is the S identifier result, which should be an address, because it's like, where's the string literal? Compile literal string. We should get this thing here, which this is just an address. Oh, it's a slice. Okay. And then of course that gets an executable. Okay. That makes sense. So we need to kind of differentiate this here. Right. So do we need a special value just for executables then? Yeah, this is like, yeah, it just adds a slice in the from executable. But I think we need more information now here. In that case. Okay. Let's just do this executable. We'll just add that. So now here, this should be executable instead. And the slice would just be like, yeah, this would just be over here. Just the value there. and then you. Okay, there we go. Let's check it out. Well, we didn't get an output, but it just exited. Okay, let's look at the, wait, there's no instructions now. Oh, hang on. So compile identifier. Yeah. So, okay, yeah. So this adds a slice. However, it's actually an executable. So we get a value back, but this should be. Let's do from value executable. Wait, slice. Yeah, we're kind of converting that directly over because it's the same thing. Just a different tag. Okay, now we get something. Okay, cool. So now we're back here. Now let's look at the compilation again. So we got set4, which is the echo thing. So we get the analog 4, set3. SF plus 0 is still wrong, I think. Yeah, it should be plus 3. Yeah. Okay, and this is wrong as well. Right. We need to, this should be plus 1, plus 2, plus 3 now because the first one is over here. And then we pop that, yeah. And then push R. Yeah. Okay. Yeah, so now we can see here the second push. No, wait. No. The first is a read-only. The second is also read-only. So this is the hello. This is the read-only. So now this works here. This S reference does work here. Yeah. And then the third one is also read-only. So there we go. We just need to fix a couple of things. Compile string literal. So first of all, this I should be I plus 1. We could also add 1 here, but whatever. Okay, so now that is fixed. The other thing was that the stack counter was not correct. So I think what's going on is that this is compiled in the wrong order again. So let's look at, where would that be? Like compile executable call. Pretty sure, because the fork should happen first, but we're saying fork and last here. So this should be first, because it kind of initializes the set a little bit. Yeah, that's all we need. and then there we go. So that should fix that. So let's do this again. Still get an error, but now this should be fixed. So now this says +3, so this is correct now. This says +1, +2, +3, so that's correct. Okay, so I think the compilation looks good now. We just need to make the evaluator be able to do these things. So it's unable to set a dereferenced register here. So let's fix that. Set where's the register? Here. So register R. So we dereference that. So it's saying that we get an unsupported dereference value type. I guess it's happening in here. So what we could do is check. Well, we could go in here first and check. So the only thing we are supporting is address. And then we're mapping that, and then we're saying that data, register, instruction ref are not supported. Stack and heap are. So what are we actually dereferencing here? Well, we're dereferencing the register R. But what does R have? It has a heap pointer. So what is the issue there? So it should be going in here. Okay. So let's do this. Could not be reference value of type or location of type. Actually, it's T. Okay. What? Oh, maybe it's over here. And what was this value? Whoops. Value of type void. Oh. Well, that does make sense. Okay, let's do this. Let's step through this to see what's happening. Okay, ref. Wait. Alloc 4. Okay. R is still void. So that is the issue. Like the virtual machine after an alloc should set R to be where the heap pointer is there. but it's not. So let's check out that. So basically the alloc instruction is not actually implemented. Well, it's okay. So the result register should be set to this. Okay, well that does explain a few things. All right. Okay. Right, we need to implement this allocation thing. So what this is gonna do is it's gonna search for a place where we can fit the allocated size, the requested size, into the heap. And I'm just gonna do the stupidest thing. Man, the problem is though, how would we know what is occupied and not? We have, so the heap is an array hash map unmanaged. So basically it's not an array, but you could use it as an array. You could loop through it's actually a hash map. And the idea is we would map memory addresses to values, right? So if, for example, if it's empty, there's nothing in it. But if you want to allocate, let's say, one value, we would try to find a value or an address that is free. However, there's no like real, I haven't defined any limitation on the addresses or anything like that, or how this is going to work at all. So let's see, how will this work? I mean, I guess maybe we could have we could just have a kind of like a leaking allocation to start with. So what we'll do is we'll say, we'll add like heap counter or current heap address. So that is the current address that is like free, I guess. We'll set it to 0. And then we'll just, as we allocate new things, we'll just increase that. so that will like, you're not gonna be able you're not gonna be able to kind of go back and like, let's say we free something. There isn't even a free instruction right now. We're just leaking all kinds of stuff. So it's like, so what we're gonna do is we're gonna say, okay, well, now we can assume that whatever address this points to, we're gonna basically have infinite memory, well, up until the limit of U size, but we're basically gonna have infinite memory from this address and up, so, or down, depending on how you see it. But so basically we could say, well, basically we just add size to this, right? If we want to have 1, we allocate 1. This should increase by 1. So next address should be like 1 that we want to have. We start at 0. And then we just return, and if this like overflows, that's going to be a crash, but it's probably not going to overflow. And then and we don't have a garbage collection, so we want to do something like in a loop that will probably crash this at some point, depending on the complexity of the program. All right, and then there's the value. So this is going to be like from address, and the address, I think it's like like it just mapped directly. So this is just going to be this, and then we'll put a defer on this. All right, yeah. So we just return the current address that we're looking at. We increase this by size, and there you go. There's our allocation. And then it's up to the program to fill this with different things. Okay. Oh yeah, and also actually, okay, maybe that's not enough. Maybe we actually do need, yeah, we need to populate probably all of those places with the thing as well. Because it's an array hash map, we should actually initialize those to be values, I think, yeah. So we have to we have to loop through from here to plus size. And this would be address then. I guess this would be an error. And then this would be like heap, put. Do we have allocator? No, so we need allocator as well. Key is address, and the value is like undefined. All right. Well, I guess the value we could initialize it to void. Okay. And then here we'll do allocator. There we go. And then we need to try. All right. Okay. So now the heap should actually be used there when we allocate. Yeah. And then when we set the heap, destination, we get the pointer. Yeah, that should be fine. Yep. All right. Okay, could not dereference location of type data. Okay, so this might be like a double dereference error where dereference too much, perhaps. Let's see what's... No, but that should be... Actually, this does make sense because we're not supposed to dereference read-only data. So that's strange. How did it become that? Alloc4. Okay, now we can see that R is 0. Oh, I see. Okay, the address is wrong. Okay, this address is wrong because the 0 refers to like, oh yeah, the first chunk of data in the address is actually mapped to read only. So this should be like data length plus, this should be like data size. This should be initialized whenever, yeah. Yeah. So this depends on the size of the read-only data. Actually, you see here, like if the address is like data end, we're dealing with read-only data. If it's like more than stack start, we're dealing with a stack, and everything in between is a heap. So well, I guess we could do no, let's initialize it here. So I did this. Sometimes you don't get like the actual the auto completion on these things. So this would be like data size. No, we don't actually have that, I guess. Oh shit, I'm running out of time here. Let's just try this. You know what? Let's do. Data size. But there's no like size we can get here. Data array list page. So the page times the page size plus the last wait. All right. So we start at data size. Oh shit, we get something. Although that looks weird. Okay. Okay, well, I don't have time now to go through this, but okay. Yeah, cool. So we got up to speed here a little bit. This is like a new thing for IR, which is getting string interpolation here to work, to be able to create these strings on the heap of the virtual machine. So I guess, yeah, we'll continue this tomorrow probably. And yeah, thank you very much for joining me here, and hope you have